Okay, we're going to finish off with the last session of calculus analysis, and it's session 8, and we're going to briefly talk about differentiation and integration. And as I said, the reason I say it's very brief is because it's not because differentiation and integration are not important. Very, very important, actually. They're one of the most used techniques in economics in the end, but the reason I'm being brief is that because I believe that a lot of you would have already learned about basic integration and differentiation, so I'm not going to stress too much on the importance of it. So what I'm just going to do is that I'm going to have a very short session just talking about like some basic techniques you remember, like chain rules and some of that, like the way to do it, and then just go along and talk about some basic fundamental rules, and then end the class, and we'll go on to the linear algebra class. As I said, note, I'll be very brief. You should be already familiar with them. If you're not familiar with the concepts, I urge you to study differentiation integration as fast as possible, because it's going to be one of the most used techniques in economics. I mean, you're going to be doing a lot of FOCs and differentiations and finding the derivative of some function to get some maximum or minimum value. So it's a very important part. So if you don't know the basic parts, I really urge you to do it. So we're going to talk about like very basic definitions like derivative of a function. The reason we're just doing derivative of a function is because as we have learned about the epsilon delta concept, the limit of function also could be defined in a similar fashion. So what this means is that we used to define function in a very vague way, but now because we know about how limit works, and we know how like epsilon delta concept works, we now can use this to define differentiation more rigorously. So it's as follows. So we're going to define a function that is real value on some interval AB, and we say that there is a limit when we say for limit. So for any x inside this AB interval, we can make a quotient as follows, which is phi. I'm not sure if I should call it phi t. I always forget about the name of the notation, but let's just say it's phi t. phi t 맞나요? 그럼 phi로 하죠. phi t로 하죠. phi t. So phi t is a quotient, which is we basically divide ft minus fx by t minus x. And because t is not x in the definition, we know that it's not going to go to 0, so it's not undefined. So in this case, we define the derivative as follows, which is basically we're taking the limit for phi t where the t goes to x. That's how we define the derivative of fx. But the important thing you should note that it's just a definition of a function. Note that in the end of the slide I wrote that provided this limit exists. This means that there are cases where the limit doesn't exist, which is very intuitive. I mean, there are cases where there's no limits, like sometimes it goes to infinity, sometimes the limits are not defined. In these kind of cases, there are no derivatives. So you should be very careful, because there are some cases where limits not going to define. Because we already know that there are cases where limits not that well defined in some cases. So in this case, we call f prime, and this f prime is called usually derivative of function. And you should be very familiar with it. I mean, in a lot of the basic calculus courses, basically what you do is just you get a function and just get a derivative and just get the answer, right? So, but this is actually what's happening in the background. So how the things are really working around. So you should know this so that it's more rigorous. And I really hope you guys all know about chain rules, but let me just like briefly talk about this again. It's like kind of related to the composition function. So what we're saying is that if a function is a continuous on AB, we say, and if there is, there's like a typo, it should be like a prime. F prime, the derivative, exists at some point x, and g is defined on the interval which contains the range of x, f, and g is differentiable, we can differentiate the whole composition function. So basically it's like the function is starting from, so what we're saying is that there's a function, there's a domain AB, and there's like a function coming from here, and then you know that the interval, which means like the image of this, is going to be in some I, right? And this I interval is going to contain the range of this function. And on this interval, we're defining another function, which is g, which is like the composition function we just explained like last session. So it's like just a composition. And if you assume that f and g are also differentiable at these points, we can differentiate the whole composition of a function. And that is very simply, we just do it as follows. So if we define the h function, which is just like a function composition of g and f, we differentiate it by as follows. So f prime is basically, we have a differentiation on the outside, so we differentiate the g first, and then we differentiate the inside, which is fx, and just multiply it. That's how we do it. I'm not going to talk about how we exactly do it, but that's how we do it. So I wrote down very basic examples that you might see, which should be also very familiar. Like for example, if you're like differentiating log x squared, there'll be a problem because you might not know how to differentiate this, because basically, but this is like this applying chain rule, because as you can see, there are just two functions combined there. So first function is the log x, which is equivalent to the g, right? So basically, we are having like a log x function as a g function, and for the f function, we're having x squared. So there's like a composition of two functions. So how you differentiate it is as follows. So basically, I wrote it in a very like complicated way, but basically what we're doing is like we're just differentiating from the outside and then differentiating also inside. So like, as you can see, there's a, so we're differentiating from the outside. And by the way, you should all know that this notation is differentiation, right? Okay, so you differentiate from the outside, and then, so it's like this. So what we get is that if you differentiate outside, you're going to get some 1 over x squared, right? So we're getting, let me just read this. So we're getting x, oh, it's longer, x 1 over x squared. We're going to get this, which is we differentiated the log function from the outside. And now we're differentiating the inside function, which is x squared, which is going to be 2x, right? And you multiply it, and you get the 2 over x. That's how you get it. But just be aware that when you're differentiating some stuff, you should be careful because we have to define where the function exists. So when we're doing this, we're kind of assuming that the x squared is not going to be like small, like 0 or something like that, because in that case, it won't be defined. We're just kind of saying it's going to be, we're only talking about derivative when it's defined. So just be careful about this, because I'm kind of assuming that this function kind of exists and its derivative is sound, because sometimes it's not. So just be careful about making derivative and limits, because a lot of the cases, because we feel like limit and derivative is like something very obvious, we just start just differentiating some function without even thinking there could be some problematic situation. And even in economic situations, it's very important because I'm not sure you'll have experienced this, but when you're taking like microtheory classes, or maybe when you're solving some equations in economics, there are cases where just differentiating makes a problem, because there are cases where there's like a corner solutions, and when some things like corner solution happens, instead of differentiating, you should first see how the overall optimization function is working. Similarly, limit and derivative cases, you can't just start just giving, you just can't start differentiating first, because there will be cases where the derivative is not defined, and which also applies to economic situations. All right, moving on fast. And some very basic things I hope you guys know, just a very brief review, which is mean value theorem, MVT. I'm not sure they abbreviate this to MVT, but I just want to make it sound very easy. So basically, in Korean, it's 평균값 정리인가요? 평균값? 중간값? 중간값은 약간 intermediate value인 것 같고, 약간 평균값 정리인 것 같습니다. 네. So we call this in Korean 평균값 정리. And what this is like basically we're getting like the, well, I mean, it is what it is, like the theorem says. We're basically getting like the mean value of a function there. So what this is, so I wrote down like a general theorem for MVT, something you should just remember and just forget about it later on. It's not that important. So basically, we're having like a two continuous function that is also differentiable and continuous. What we're getting is that there's some point in the middle, A, B, such that this sort of things hold. And you might think, what the heck is this? I mean, I don't remember these kind of MVT function, right? But these kind of MVT theorem is not used to you, because you usually use for like more specific case for MVT, which is second definition. So when we have the case where instead of having G, we just have like a variable b minus a. So basically what we're doing in this case is that the first case we defined more generally by talking about the g as a function, but in the second case we just made it into gx is x, right? So this is just similar, but the only difference is just that this becomes like, you're defining like the g function as just like an identity function. I'm not sure how you should call that. So like gx is x, and you just get this, right? The same thing. So basically, what we're saying is that for some endpoints b and a, if you subtract the function, the value is going to have some sort of mean value using the function's derivatives right there. So, and you might wonder where we use this actually. So, and one of the things we use it is to see how the function overall behaves. So, for example, some sort of things like this. So, I think you should be very familiar with this concept, like seeing like whether function has a maximum value or whether it like the slope rises or has a minimum value at some point. We usually use, what we do is we differentiate the function and see their behaviors, right? Similarly, the one way we use mean value theorem is to make them help us tell about what function is and how it behaves. For example, I wrote here, so if we believe that the f function is differentiable at a-b interval, and if for all points inside this a-b interval, if the differentiable function, I mean the derivative function is non-negative, we say that f is monotonically increasing. So if you remember, right, you should remember like the cases where the function, you know, when you have a differentiation, and these are the cases where the function, if it's like monotonically increasing, if we make a derivative, it's going to be like positive, right? And you can use the derivative to show the behavior of function. And also similarly, if the function is monotonically decreasing, if you differentiate the function, it's going to give you minus. Which shows by differentiating, you can know how the function operates. And it's very important because like for a very basic cases like this, you might think that why are we using this? But when you're solving like maybe mathematical questions, you might be working with a lot of functions that is more complicated than this. And you might want to know like the behavior of the function. And because the function itself is very difficult, perhaps sometimes differentiating the function lets you know more about the function's behavior. That's why we kind of do differentiation. And if it goes on, we do like second order differentiation and all that stuff. But that's how we do it. It's because if the function itself is very difficult, and it's kind of hard to see how it behaves, differentiating tells you more about the function. That's why we do this. And so I told you like where we use mean value theorem. One of them is using here. We use it as a proof. So you can look at the proof there. So basically, this is mean value theorem, right? Here in the bottom. So what we're doing is that we're just taking 2 points, and we can do the mean value theorem. And because in this case, like the f is multiply increasing, it's always positive or negative, the derivative, we can kind of use this to show that f is multiply increasing for any x2 and x1, right? So that's how it works. So. And integration, very short, because most of it's very redundant. I'm just going to talk about very basic definition-ish. I mean, to be more exact, I'm just going to talk about the fundamental theorem of calculus, because I think that's the one you should just remember. And other thing, just differentiate like how you do, like differentiate, like you're already better than me. Like differentiate x squared, you get this, you know, all that stuff. And integration by parts and integration by substitution, right? All that techniques. Even I don't remember it, so I always Google it. But those techniques are like, they're important, but I don't think they're like that important because I think you should like be already used to this. So I'm just going to talk about a very important theorem here, which is, well, fundamental theorem of calculus. So I divide into 2, although usually we call the second one to be fundamental theorem of calculus, I think. Like number one is like, it's used more like a start of the fundamental theorem. So you should be very used to this. What is this? It's basically, for now we thought about differentiation and integration. And sometimes if you just think of it in other ways, we think like they're like different processes, like they're totally separate things. But what fundamental theorem tells us is that actually they're the same thing. I mean, not same, but they're kind of like inverse processes. So, I mean, even in historical sense, like in the mathematics, in calculus, integration and differentiation has different roots. So it started on a totally different path, but later on they realized that actually those two are just like an inverse process. So that's why it's called fundamental theorem calculus. So I'm going to call this FTC. So FTC1 is very simple. So basically, we say if f is integrable, 적분 가능, on AB, and then we can put fx as follows. So basically, we're kind of integrating from a to x, right? The function. Then we can say that f is actually continuous on AB. And also, if f is continuous, then f is also differentiable at a0, x0, and we just write it like this. So you should be kind of familiar with this concept. So basically, we're defining the function like we start from a to x, where x is like the variable we can move on to show like we're just differentiating from a point to x, right? And in this case, what we can do is that in this case, f is becomes continuous, and the f is continuous because it's differentiable. And what we can do is basically can just get a differentiated function. So this is the first start of the fundamental theorem. And from this fundamental theorem, we can use this, and we can go on to the second one, which is actually more fundamental and important part, which is basically it shows that the integration and differentiation is an inverse process. So basically, if f is integrable in AB, and there's a differential function f, where we get that the differentiable of the big F is a small f, then we get this notation, which is basically fs is from a to b integrated by, and we get fb minus fa. And this is very important because I didn't talk about very tedious part about how we do integrations, but if you really want to do integration using the very basic definition, it's very complicated because you have to basically make parts of the function, and then you have to send it to the limit to get the whole area of a function, if you remember how to do the integration. But you can't do that every time. But the good thing is, using this fact, we can actually do integration as if we're using like a differentiation concept, and just subtract fb to fa to get the differentiation, to get the integration value. So that's why it makes life a lot easier. Because otherwise, you do something like, if you want to do like differentiation of f, like from A to B, what you have to do in the past, like very long time ago, would be you just really do this sort of partitioning and just get the values and just add it up the sums, and you have to send the n to infinity and see how the limit tends to, which is very more complicated, especially if the function is very more difficult, more complex functions, right? But this was solved using the FTC. I just wanted to point that out. But roughly, this just means that differentiation and integration is just an inverse process. So you should just remember this as follows. Okay, so basically our analysis course is kind of ended for review. But I just want to talk about just like two functions that you might not be familiar with, but you'll see this function a lot, which is two functions, exponential functions and logarithmic functions. And some of you, especially if you're from undergraduate economics courses, it's possible that you might not be familiar with some log function or exponential functions, because a lot of these functions are usually dealt with in what I call this, engineering mathematical department. So you might not see them in economic courses, but they are very useful functions, so you should know them. So, very briefly talking about them. So what is exponential function? It's a function of the form we call y is 2x. I'm just going to say 2x. No, ex, sorry. Y is ex. So what is this? So what is the number e? So you might not know this number. You don't have to know too much about how this number works. But just remember, just out of curiosity, this number e is just a number defined like that. So it's basically like summation of 1 over n factorial. Does everyone know like what factorial means, right? factorial means like you're just multiplying from 1 to n. So like, in case you don't know, like n factorial basically means you multiply from 1 to n, like that. So basically, E is defined such that is a summation, is an infinite summation of n over 1 factorial. So you don't need to know too much about how this works. If you want to know about E, you can check the textbooks. But basically, this is what E is. In English or Korean, I think you call it 자연상수 or something. Although I heard it's a bit misleading term because 자연상수, there's no something as natural constant, but still, in Korean you sometimes call them 자연상수, I think. And sometimes for convenience, we sometimes write EX as EXPX. They're the same thing. But we sometimes do this because for the exponential functions, there are cases where you have to put a lot of things on the equations, like we just did this, but there are some cases where you have to put like a lot of things here, like log x plus log y, something like this. Sometimes then it becomes really hard to write this, right? So instead of doing E, we just go EXP and just put everything inside the parentheses. That's for notational convenience. So what does this do? I just wrote down some very nice properties of exponential function. We kind of use them because EX has these nice properties, which is, so we're going to define EX on R, then, well, EX is continuous and differentiable, which is very nice quality because we really like functions if they're continuous and differentiable. So they're a very good thing, good quality. So they're basically kind of saying that the function is very smooth, in a sense. And also, very interesting property is that even if you differentiate EX, you still get EX. So very interesting function because even if you differentiate the function, you're just going to get the same element, which is very, very nice property because sometimes we differentiate some function because it becomes really dirty or complicated, but this case, they solve your problem. They help you. And also the third quality is EX is strictly increasing function and EX is positive. And you can see this actually if you draw the exponential graph. The exponential function kind of goes like, it's like kind of like an increasing function like this. I should write here too. And it kind of goes smaller, but it never goes to 0. I mean, it does go to 0, but it never touches the horizontal bar, and it keeps on going up for the right-hand side, which kind of shows that it's just a positive function. And the four is also very nice quality. Is that basically you can do, if you multiply exponential functions, you just need to add up the upper parts, right? So if you're multiplying EX and EY, you're going to get EX plus Y, which is also very nice quality because you can basically sum up the equations. So that's why we kind of use exponential function a lot. And the fifth quality is that as EX goes to infinity, EX goes to infinity as X goes to infinity, and EX goes to 0 as X goes to minus infinity. You can see from the graph, if X goes to infinity, it goes to infinity, and if X goes to the left, it's going to go down and down and going to go to 0, right? Also very nice quality. All right, moving on. You should have kind of guessed that also that EX and exponential function and logarithmic functions kind of inverse because look at the number 4, like EXY being EX, EY is X plus Y. You kind of remember how we used to remember the logarithmic function where you kind of, if you do summation, is same as multiplying them, which is actually true because it is inverse processes. So because EX is an increasing differential function, you can kind of assume that it's going to have an inverse, right? Because one-to-one functions have inverse. And we call this inverse function actually as logarithmic function. The basically log functions and exponential functions are just two different, same thing in an inverse way. So this is a relationship. So it's defined as follows. So basically like that. So e to the power of log y is going to be y. Or we define them as log 2x. I keep saying 2, I don't know why. Log EX is X. where x is real. So basically, if you're familiar with the concept where the log has a base 10, you can think of it like this. So basically, log function this one has base e. So what it is that because log e and ex, if you remember the computation, the x can go down, right? So you would have like x log e. And even for base 10, remember like it all says 10 is 1. So basically this becomes 1. So you only have x left, right? This is why. So I'm pretty sure if you're in undergraduate or you're in high school, if you learn about log functions, what you see is that you usually talk about log function where the base is 10. But from undergraduate and graduate schools, when you talk about logarithmic function, almost 99.9% of the time, you're talking about the log function with the base e, not 10. So just remember that. So differentiating the equation 12 is going to giving us the function like that. See? So basically, what we can do is that to this to show that actually the differentiation of log y. So remember, like when we did the logarithmic derivative. Remember, like when we divided log x squared in the past session, we went like this, right? This is because of this quality where if you differentiate the log, basically what you have to do is you have to just have 1 over y. So basically you make a division on this, although y has to be bigger than 0. So that's why we did this, because if you differentiate the log, what you need to do is you just put this part in the denominator and just put 1 on the denominator. Very nice quality too. Everything okay so far? Okay, so I hope you guys already know this, but there are properties that is very nice for logarithmic function, and we're going to end the class with this one, which is the first one. Surprisingly, if you add up the log, you just need to multiply them. So log x plus log y is basically log xy. And also for log x, I'll just draw it to make sure. You can kind of assume that because log is an inverse process of exponential function, remember the exponential function went from like upper way, like it's like a U shape. It's an inverse U shape for a log function. So log function is more like a 0. It's like this, right? But be aware of the part because unlike the exponential function, log function is not defined in the negative parts and 0. So just be aware of that. So it's just like has an inverted U kind of shape. So then you can kind of see that. Oh, I wrote it like it's not gonna diverge. It's kind of like this. It's gonna go up very slow. So as x goes to infinity, log x also goes to infinity. And interestingly, if x goes to 0, log x goes to minus infinity. Very interesting property. So, and you can kind of see like comparing with the exponential function and logarithmic function all goes to infinity, where x goes to infinity. You can kind of see that exponential function goes to infinity faster because exponential function is going like this, right? And logarithmic function is also increasing, but it's increasing more slowly. That's why, for your information, a lot of the when you're doing economic research, sometimes there are variables that have very high value sometimes. So in that case, what you do is that you transform the values by doing logarithmic transformation. Because if you do logarithmic transformation, you can make a case where if there's too much, there's some variables that are too big, you can use log to kind of adjust it to kind of see the distributions. So a lot of the time, especially if you're doing like labor economics, and if you're dealing with like wages, for example, there are cases where when you draw the distribution of wage, there's going to be like few people that's going to have really big wage. In that case, what you do is instead of using the raw value, you take the log to make the value to be more normal distributed shape. So it's just information. Because what logarithmic function kind of does is just that it kind of underestimates the big values because it's not increasing fast enough, right? Just for your information. Okay. And lastly, number 4, which is basically you have log xa, and the A goes down. So that's a very nice property of log function. So if you have log x squared, you get 2 log x like this. Should be familiar with you. That's how it works. So logarithmic function, exponential functions are used a lot in analysis. So it's very nice if you know about like how it operates basically. And for the people who are watching the videos, the attendance code for today is 33, right? 33. So it's 33. Okay. Okay. So that was the end of the analysis calculus review course. And we'll have like 10 minutes break. And after that, we'll be moving on to the linear algebra. Okay. 10분 쉬었다가